All right, so this is Chapter 5, Section 2, Polynomials, Linear Factors, and Zeros. That's 3 different things you can write in your summary about. We have 2 learning objectives: to analyze the factored form of a polynomial and to write a polynomial function from its zeros. Do not have to write this down, but I found it worth mentioning. If p of x is a polynomial function, the solutions of the related polynomial equation, p of x equal to 0, are the zeros of the function. Finding the zeros of a polynomial function will help you factor the polynomial, graph the function, and solve the related polynomial equation. So we're going to take a look at polynomials and find the factored form of x cubed minus x squared minus 12x. So you guys are in Algebra 2, which at this point in your mathematical career, we take certain shortcuts, like what do each of these terms have in common, what item. And so I'm going to show you here, you don't have to write this down, but I'm going to show you the Algebra 1 way to look at it. So if x cubed is x times x times x, x squared is x times x, and 12x is 12, it is 2 times 2 times 3 times x. Which factor do each of these have in common? They each have an x. So when I factor out an x, I am left with x squared. I am left with a negative x. And I am left with a negative 12. Now we're here in quadratic land. Which 2 numbers multiply to give you negative 12 and add to give you negative 1? So negative 4, positive 3. The bigger number has to have the negative sign so that you get negative 1. So when it's asking what is the factored form, you want to make sure that you pull out to the front any common factors, write down what's left, and then try to factor that if it's possible. Sometimes it won't be possible, sometimes it will. We have to, unfortunately, remember the stuff from the previous chapter on factoring quadratics, difference of sums, and difference of, I said that right, difference of squares, difference of squares, there you go. I'm remembering from chapter 4. So you have to bring in those skills that we worked on last chapter. You can't just dump the delete button in the brain and forget all about them. They're going to keep coming back around in this section. All right, so I'll highlight what I want you to write down. This is a lot of stuff going on, so let me get out my highlighter. So roots, zeros, and x-intercepts, which are all 3 the same thing. Roots are zeros, are x-intercepts. Not y-intercepts, x-intercepts. So these 3 things are the same. X minus b is a factor of the polynomial p of x. B is a 0, b is a root, p is an x-intercept. All right, so our sample problem for this section is what are the zeros of y equals x times x minus 3 times x plus 5. And then we're going to graph the function. So the zero product property, all the way back in chapter 1, says that the products, if the products of an equation are 0, then each component can equal 0. So we are going to say each piece here, here, and here is equal to 0. So we're going to go x equals 0. We're going to go x minus 3 equals 0. And we're going to go x plus 5 equals 0. The answers to these three equations are zeros of our function. So this is one of them. Thankfully, no solving involved. I add 3 to both sides. This is a second 0. And then I'm going to subtract 5 from both sides. And my third 0 is x equals negative 5. Alright. So we know the zeros are x equals 0, x equals 3, and x equals negative 5. We need to find points for our x values in between each of our zeros. So I'm going to make a little table, have my x values, and I'm going to have my function. So that way I know, am I above the x-axis, am I below? And I can start putting points so we can have the turning points, etc., etc. So I want a point in between 0 and 3. I'm going to pick 1 because 1 is a really easy number to calculate stuff for. And then I want a number between 0 and negative 5. So I'm going to go ahead and say negative 1.
Wait. Oh,
Because you just, anywhere in between. So between 0 and 3 and between negative 5 and 0. So if you list these in order, I want one that's in between these two and one that's in between these two. So I picked 1 and negative 1. So I'm just going to take my equation and I'm going to plug in 1. And 1 minus 3 is negative 2. And 1 plus 5 is 6. 1 times negative 2 times 6 is negative 12. And then negative 1, so I'm going to do the same thing except negative 1. And I get negative 3 minus, or sorry, negative 1 minus 3 is negative 4. And 1 plus 5 is, sorry, negative 1 plus 5 is 4. Negative 1 times negative 4 is 4 times 4 is 16. Determine the end behavior. So if I were to multiply this x, if I were to multiply these together, I'd have a x squared plus 2x minus 15. And then if I were to multiply that by x, I'd have an x to the third. So I have a cubic function, so an odd-powered function that has a positive coefficient. So if we look at our chart from yesterday, that means a down, up. So our end behavior is down, up. All right, so we're going to use the zeros, the additional points, and the end behavior to sketch our graph. Okay, so let's put all of our zeros down. I'm going to put those in green. So x equals 0. There's one right here. There's one at 3. And there's one at negative 5. 1, Okay, so I know my graph is going to cross. It's going to go up and down and up, up and down. We have these, the other coordinate, 1, comma, negative 12. So I'm going to over 1 down 12. Yeah, right there. And then I also have negative 1, 16. Of course. 11, 12, 13, 14, 15, 16. Negative 1 is 16. Way up here. Oh, he's got a curvy. Okay. So I plot those points, and then we're going to use our end behavior. So our end behavior says we start down, punch through our 0, come up to this point, come back down, come back up. Looks like, well, my picture looks like an M. Made a graph. Take out a highlighter and highlight these 4 steps, because when they ask you to find the zeros and graph the function, they're going to expect you to follow these steps. Determine the end behavior, and then put them all together. All right, the factor theorem. The expression x minus a is a factor. So I'll highlight the important pieces. X minus a is a factor if and only if a is a 0. So if you find your 0, whatever a value that is, then you can always say x minus that number is going to be a 0. It's going to be a factor of your function. So if we are given the zeros of our polynomial, we can put together that polynomial. So if I look, what is this first question here, what is the quadratic polynomial function with zeros 3 and negative 3? So quadratic means I have to have an x and an x, because when they multiply together, they give me the x squared. And then my zeros are 3 and negative 3. So I'm going to go x minus the first 0, and that's x minus a, and x minus the second 0. Translated here, though, it's going to look like x minus 3 and x plus 3. Then we multiply that up. X squared plus 3x minus 3x minus 9 gives us x squared minus 9. We can do the same thing and make a cubic function. Just the foiling is a little more intense. We want to make a cubic function, so we are going to take the opposite of each of our zeros. I'm just going to go ahead, write this as an x minus 3 squared. We had a little formula that told us if we have a binomial and we square it, that it's the same as the first term squared, the double the first and the second term multiplied. So negative 3 times x is negative 3x, and then we double that, it's negative 6x, and then the last term squared. That was from a couple chapters ago. And then all I have to do now is multiply each of these terms by x. and then multiply each of these terms by 3. Plus 27. And then just combine my like terms and I get x cubed minus 5x squared because negative 6x squared. Oh, that's 3x squared.
Yeah.
Hello, handwriting. Negative 6x squared plus 3x squared is negative 3x squared. I'm going to cross these off as I fuss with them. Negative 18x. And 9 plus 27. Math is all crazy today.
Wait, I think it was 3x squared.
Because I did 3 times x squared. Everything in here got multiplied by 3.
No, so you multiply by x.
Yeah, so this should be
x.
9. This is x cubed. X times x squared is x cubed.
Oh, there's
X times negative 6.
Separate.
Negative 6x squared. X times 9 is 9x, and that's where my error was in my math. 3 times x squared is 3x squared. 3 times negative 6 is negative 18x. 3 times 9 is 27. Okay, so now I'm on 9x minus 18x gives me minus 9x's. And then the 27, he's all hanging on the end. All right, so when you have, like we did here, we have 3 as a 0 twice. So that is called a multiple 0. It's a repeated linear factor. And when we have a multiple 0, it kind of changes the way our graph looks. So if A is a 0 of multiplicity n, and the polynomial function y equals p of x, then the behavior of the graph at the x-intercept A will be close to linear if n equals 1, close to quadratic if n equals 2, close to cubic if n equals 3, and so on. So we look, which n are they referring to? They're referring to the power. So if n equals 1, like you just have power of 1, x to the 1 is linear. X squared is quadratic. X to the third is cubic. They're just saying when you have a multiplicity, and wherever your x-intercept is, at that place, it'll look like a line if your n equals 1. It'll look like a quadratic. If n equals 2, it'll look like a cube. So let's see how that looks with an example problem. The first thing we're going to do is find the zeros of f of x equals x cubed minus 4x squared plus 4x. So in this case, what are their multiplicities? So we find the zeros, find the multiplicities. How does the graph behave at the zeros? So we are going to first factor, and I can see that there is an x in common for each of these terms. So I'm going to factor out an x. When I do that to x cubed, I get x squared. When I do that to negative 4x squared, I get negative 4x. And when I do that to 4x, I get plus 4. So we need two numbers that multiply to give us 4 and add to give us negative 4. Leaving negative 2 and negative 2. I need to make sure I rewrite this so I can see my multiplicity. So this is the same as x times x minus 2 squared. So my zeros are at x equals 0 and x minus 2 equals 0. So x equals 0 has a multiplicity of 1. Only one of them. X equals 2 has a multiplicity of 2. So when we put our graph together, we're going to cross at 0, 2. And we are, the behavior that is going to happen at our multiplicity is going to look like a cubic. All right, so I have to correct, n is not the highest degree of the polynomial. N is the multiplicity. So for x equals 0, I have a multiplicity of 1, so it's going to look linear. My graph is going to look linear at that 0. When I have a multiplicity at 2 of 2, then it's going to look like a quadratic. So if you graph these,
Why is x equals 0 multiplicity of 1?
how many x equals 0s do we have? It's I got a power of 1. This has a 2 of them, so it's multiplicity of 2. Good question. Okay, so when we look at our graph, at 0, it looks like a linear function because our multiplicity, we only have 1, 0. If it were x squared instead of x equals 0, it would look like a parabola. So at x equals 2, we do look like a parabola because we have a multiplicity of 2. And that's how multiplicities dictate what your graph is doing. All right. All right, so to make a sketch of this picture, a nice little cubic function. Sometimes within a function, we're going to have a relative minimum and a relative maximum. Unlike a parabola where we go, yeah, that vertex is definitely right at the minimum. For a cubic function, these points are important, but technically this is not the minimum of the function because our function goes all the way to negative infinity. Same with the maximum. This is an important point on our function, but it is not the maximum of our function because our function goes all the way up to positive infinity. So a relative maximum is the value of the function at an up to down turning point. So the relative maximum happens at a turning point when you're going from up to down. And a relative min is the value of the function at a down to up turning point. And we're going to graph the max and min of our function f of x equals 3x cubed plus x squared minus 5x. And we're going to go ahead and use a graphing utility for this. All right, so using our graphing utility, we graph 3x to the third plus x squared minus 5x. And we get turning points at negative 0.865. This is the relative max, comma 3.132. And then the relative min is at 0.642, comma negative 2.004. So that's our relative minimum. All right, here's our word problem. The design of a digital box camera maximizes the volume while keeping the sum of the dimensions at 4 inches. If the length must be 1.5 times the height, what should each dimension be? Take a moment to write down the important information. My first step in anything that I do is I like to draw a picture because I'm a visual learner, so it's very helpful. So we have a box. It has a length, a width, and a height. And our first step is to define our variable. So we're going to let x equal the height of the camera. So I'm going to replace the h with an x. And then it says the length must be 1.5 times the height. So the length is, so I'm going to replace length with 1.5 times the height. So the width, if we know that the sum of the dimensions is 4, so that means 1.5x plus x plus whatever my width is has to equal 4. Then I can say that the width is equal to 4 minus 1.5x minus x, or 4 minus parenthesis x plus 1.5. And that reduces down to 4 minus 2.5x. So I just took the property that the sum of the dimensions is equal to 4. And I got everything in terms of x. So we can replace our w with 4 minus 2.5x. All right, so the question is, we want to maximize the volume. So if volume is length times width times height, let's put that equation together. The length is 1.5x. The width is 4 minus 2.5x. And the height is x. We're going to graph this polynomial function and find the relative maximum. So we got 1.5x (4 minus 2.5x) and x. So let's take a peek at our graph. So go ahead and sketch this graph on your paper. I'm going to take a little picture of it so we can put it on our presentation. So when we look at the graph, it doesn't make any sense to look at any values less than 0 because I'm talking about distances, lengths, widths, heights, and it doesn't make any sense to have a negative length, a negative width, or a negative height. So I'm going to completely ignore what happens below 0. My volume is negative after this point here on the graph. So I am not going to look at any values that are x values greater than our intercept. We are going to look at the maximum. It happens when x is equal to 1.067. We want to know the design of camera maximizes the volume. What should each dimension be? So if my x value is 1.067, then my length is 1.5 times that. 1.5 times 1.067, which is 1.6005. And then my last one is 4 minus 2.5x. And if x is 1.067 times 2.5 equals, make that negative, and add 4 to it, 1.3325. And those are all in inches. And that's all for today.